Okay, geometry section 7.2 gets us into quadrilaterals, specifically parallelograms here. And we're going to be talking about quadrilaterals for the rest of chapter 7, and parallelograms are a great place to start. So we begin with our definition of what a parallelogram is. It's a quadrilateral with two pairs of parallel sides. So in this figure that I've got right here, guys, this is a pretty good example of what a parallelogram looks like here. It basically, somebody described to me once as kind of a slanty rectangle, and that's pretty good. The key to a parallelogram is that this side on the top has to be parallel to this side on the bottom, and then over here on the left and the right, these two sides have to be parallel as well. So that's the definition of it. It's a quadrilateral, meaning it's a four-sided polygon, and it's got two pairs of parallel sides. There's a symbol that we use for parallelogram that, just like a triangle symbol, is the shape itself. So we would call this parallelogram ABCD. You can actually start naming this from any point that you want. So ABCD isn't the only name for it. You could call it, for example, parallelogram. I could choose to start from point C. And then from there, you can go either clockwise or counterclockwise, but you need to go in the same direction once you get started. So if I wanted to start at C and then go to point B, that's the last choice I get to make. The next point would have to be A, and the fourth one would have to be D. So there are, if I'm not mistaken, 8 different ways of naming a parallelogram here, and this is just one or two of them right there. So that's what a parallelogram looks like. Now, the definition of it is given right here, the two pairs of parallel sides. But there are 4 important properties that go along with parallelograms as well. And you might have been able to deduce some of those just by looking at the figure right here. But we don't need to deduce. There are 4 theorems here that go along with parallelograms to give us some extra information. So they all begin with this general statement right here. If a quadrilateral is a parallelogram, then theorem 7.3 right here tells us that the opposite sides of a parallelogram, if we go back to this diagram right here, are, well, you might be tempted to say they're parallel, and you're right, but we don't need a theorem to tell us that, because that's already given by the definition. This property, this theorem right here, tells us that in addition to being parallel, opposite sides of a parallelogram also have to be congruent. Okay, so anytime you make yourself a parallelogram, whatever it is that it looks like, if you've drawn it properly, I'll make this one go the other direction, it should always be the case that these two parallel sides are congruent to each other, and these two parallel sides are congruent to each other as well. That's information that was not given to us here in the definition of a parallelogram, so we need a theorem in order to tell us that. Okay, theorem 7.4 now turns our direction to angles within the parallelogram. And in this theorem, it asks us to look at opposite angles. So we'd be talking about this angle right here and the angle that's in the opposite corner from it, which would be this one right over here. And we're not going to make this take too much time here, guys. These two angles here, as you might have guessed, are going to be congruent to each other as well. All right, so opposite angles in a parallelogram are congruent, and I really could say the same thing about this angle here in the top right corner and this angle here in the bottom left corner. Now, all of that is based on the idea that if you were to draw one diagonal throughout a parallelogram here, you end up creating 2 triangles that are congruent to each other. I think you can kind of tell that by looking at the figure right there, and because those 2 triangles are congruent, we know that these 2 angles have to be congruent, and so on and so forth. But I don't want to get too deep into this here as far as proving these theorems here, so we'll just leave it at that. Now, theorem 7.5 is one that's probably less obvious than the others. Consecutive angles are. So in this case, we might be talking about angle Y right here and angle Z. Now, you don't want to trust your eyes too much, but it certainly looks to me that angle Y is probably acute and angle Z is probably obtuse. Now, if that's the case, there's no way that angle Y and angle Z can be congruent. The only other relationship we've really talked about throughout this year is that very often, if you have one angle that's acute and one of them that's obtuse, very often those 2 angles are supplementary, which is going to mean that they have to add up to 180 degrees. Now, the reason for that, guys, really deals with the fact that, let me shrink this down for just a second and move things around a little bit. If you remember this diagram from way back in chapter 3, two parallel lines here cut by a transversal, one of the theorems we learned there is that angle 1 and angle 2 would have to add up to 180 degrees. Measure of 1 plus measure of 2 is 180. Well, now I think you guys can see without too much difficulty here that if I drew a second transversal that was parallel to the first one that I drew, this line here would be parallel to this line here. Well, sure enough, we have created a parallelogram right there. It's a four-sided figure with two pairs of parallel sides. And so, if this statement was true back before we had that purple line in there, it still has to be true right now. So that's where this third theorem comes from, and those are the three things we want to make sure we understand about opposite sides, opposite angles, and consecutive angles within a parallelogram. Now, there's one more here that I think is probably less obvious here, and it starts the same way as the last one did, guys. If a quadrilateral is a parallelogram, then Theorem 7.7 tells us something about the diagonals of that parallelogram here. So let me go ahead and use an actual parallelogram here that I made with the Smart software because I want this to look pretty accurate here. What happens with the diagonals of a parallelogram? So let me try again. I want to make this look pretty good here, guys. I can probably make that a little thinner there. And if I were to draw the two diagonals of a parallelogram here, that would be one of them there, and the second one, ooh, that looks pretty good, would look right about like that. Okay, what's going on here, guys? Again, I won't bore you too much with the details here, but you've created triangles here that are congruent to each other. For example, this one triangle right here on the top ends up being congruent to this one triangle down here on the bottom. And what that does for us is it means that this piece right here has to be congruent to this piece. And similarly, this piece right here, we would call that a half diagonal, is congruent to this one as well. So what we would say here in Theorem 7.7 is that if your quadrilateral is a parallelogram, the diagonals bisect each other. Okay, that means, another way to phrase that right there, we might want to put this in the same spot right there, that the two diagonals share a common midpoint. Okay, that's what that means. Now, to be really clear, that does not mean that the four pieces that I have marked there with blue tick marks are all the same. But if I were to just make up a number and tell you that this piece right here had a length of 8, that would mean that this piece in the bottom right would need to be 8 as well. It does not mean that the other two pieces of the longer diagonal, the one that goes from here to here, they don't need to be 8. This piece might have a length of, I don't know, 13. It looks longer than the 8 to me, and that would mean that this one would have to be 13 as well. But it is not the case that these two pieces have to be congruent to each other. In fact, if they are, you're dealing with a very specific type of parallelogram, but we'll get into that in a couple of sections, so we don't need to deal with that right now. Okay, guys, so what we've seen so far is the definition of a parallelogram, two pairs of opposite sides that are parallel, and then four properties of parallelograms. The opposite sides must be congruent, the opposite angles must be congruent, consecutive angles must be supplementary, and the diagonals bisect each other. And the good news is, you guys, that's all of the new content here in section 7.2. Everything we're going to do now in terms of solving problems is just going to use one of those four statements right here. So I've got four problems for you here. They should go pretty quickly. We're going to solve for x in each one. So the first thing you'd want to ask yourself is, what kind of shape are we dealing with here? Well, those red arrows show you that you have a quadrilateral with two pairs of parallel sides, so this is definitely a parallelogram. I wouldn't know that without the red arrows. And what have we been given? One side length up here on top and one side length down here on bottom that's parallel to that first one. So to do this one, guys, we're going to need to go back right here to Theorem 7.3 that says that opposite sides in a parallelogram are congruent to each other. So you don't need to write this down, but it's not a bad idea to write Theorem 7.3. That's kind of our guiding light on this problem right here. Opposite sides in a parallelogram must be congruent. So I'll take my top, 5x plus 15, and set that equal to our bottom side, which is going to be 8x plus 3. I'm going to move the 5x over to the right, and then at the same time, I'll move the 3 over to the left here. So those cancel and those cancel. The 15 minus 3 is going to get us a 12. That is going to equal 8x minus 5x is a 3x. Divide both sides by 3, and we're going to get x is equal to 4. And if I really wanted to make sure we had this right, let's plug that 4 back in there, guys. 8 times 4 is 32, plus 3 is going to get us 35 for the length of the bottom side. And up on top, we should see the same thing. 5 times 4 is 20, and 20 plus 15 is 35 as well. So again, Theorem 7.3 tells me here, guys, that opposite sides in a parallelogram must be congruent, and that's what this one seems to suggest. So, feel pretty confident about our answer there. Okay, let's move on to a different example here. In B, again, do we know we have a parallelogram? Yes, we do, because it's a four-sided figure. We can clearly see that, and we can see two pairs of parallel sides on opposite sides of the figure because of the red arrows. But now, instead of sides, we're dealing with angles. One angle up here in the top left and one here in the bottom right. That's what we would call opposite angles. And I do believe we learned a theorem here about opposite angles in a parallelogram. That's Theorem 7.4, which tells me that in a parallelogram, your opposite angles must be congruent. So Theorem 7.4 is what we're going to use in this problem. Opposite angles of a parallelogram must be congruent. And what does congruent mean? Having equal measure. So the 11x minus 4 has to equal the 6x plus 46 we had in the bottom right corner. So that's the hard part here, guys. And beyond this, this is just Algebra 1, which you guys have been doing for years now. Nothing should surprise you here. I'm going to add the 4 on both sides here. Those cancel, those cancel. 11x minus 6x is going to be 5x, and that's going to equal a 50. We'll divide by 5 now and get x equals 10. And just to make sure we've got this right, let's plug it back in there. 11 times 10 is 110, minus 4 is going to be 106 degrees. And in this bottom right, 6 times 10 is 60, and 60 plus 46 is also 106 degrees. So I feel really good about that answer there as well. Okay, so those are two examples using Theorems 7.3 and 7.4. Let's take a look at the next one. Again, do I know for a fact that this is a parallelogram? We do, because the top is parallel to the bottom, and the left is parallel to the right. So I can clearly see this is a quadrilateral with two pairs of parallel sides. But now we're dealing with two angles here, one in the upper left and one in the upper right. Those two angles, you'll notice, are not opposite angles the way we were dealing with in the previous problem, but they're right next to each other here. And that means we're dealing with consecutive angles. And one of the theorems we wrote, this one right here, Theorem 7.5 tells us that in a parallelogram, consecutive angles are supplementary. And what does supplementary mean? They have to add up to 180 degrees. So, something weird happened with that angle right there, but we're going to add these two together. 7x plus 13 has to be added to the 4x plus 2, and that sum now has to be 180 degrees. So just following theorem, this was Theorem 7.5? It was. So Theorem 7.5 is what we're using here. Let's combine some like terms. 7x plus 4x is going to get us 11x. 13 and 2 is going to be a plus 15. That equals 180. We'll subtract that 15 from both sides now, and we will get 11x is equal to 165, and then we'll divide both sides by 11. I would think most of us would grab our calculator right here, but I'm pretty sure you're going to end up with x is equal to 15 for your answer. So if we check that one, this might be a little bit more complicated here. Let's see what we can do. 7 times 15 is 105. Adding 13 to that, I believe, is going to get us a 118 degree angle right there. This angle, 4x plus 2, 4 times 15 is 60. 60 plus 2 is 62 degrees. And what we should see now is that when we add 118 plus 62, 8 and 2 is 10. carry the 1, 1 plus 1 plus 6 is 8, and bring the 1 down, we get 180 degrees, just like we expected. So confidence is high in that answer as well. And one last example for you, and I bet you guys could probably figure which theorem this one is going to use. This diagram looks a good bit different than all of the other ones that are out there, guys, because now for the first time out of these 4 examples, the diagonals of the figure have been drawn. Now again, we know this is a parallelogram because the top is parallel to the bottom and the left is parallel to the right. So it's definitely a parallelogram, and the diagonals have been drawn here. And what's going on now is the length of one of these half diagonals is 5x minus 17, and the other half of the same diagonal is 3x minus 3. So if we were to jump back to theorem 7.7, that's the only theorem here that deals with the diagonals of a parallelogram, and it tells us that those diagonals bisect each other. So if this piece was 13, this piece would have to be 13. The two halves of one diagonal have to be congruent to each other. So we would set 5x minus 17 equal to 3x minus 3. Okay, let's solve that and see if we like what we see at the end here. So minus 3x, and we'll add a 17 on both sides as well. Those terms cancel. Those terms cancel. 5x minus 3x is 2x. And that equals a negative 3 plus 17, which is 14. And divide by the 2, we'll get x equals 7. So I think that's my answer. Let's plug it back in and see what we see. 5 times 7 is 35, and 35 minus 17 is 18. And how about over here on the right? 3 times 7 is 21, and 21 minus 3 is 18 as well. The two halves of one diagonal have to be congruent to each other, and that's what it looks like happened here. So feel really good with that answer as well. Let me take just a second and add one more little thing to this. You guys don't need to write this down, but I do just want to warn you because I think this shows up on your homework here at some point. If you ever saw a problem like this, okay, where something like this was drawn and something like this was drawn. Let me just say we're dealing with A, B, C, D, and that this point right here was E. What if I gave you something here, guys, like AE was, I don't know, I'm just going to make some things up right here, 3x plus 5, there you go. And they told you down at the bottom here that the length of AC was, and I'm just kind of guessing here, something like 7x, let's see, 7x minus 3. Let's go with that. In a case like this, it's a little bit tricky because you've been given the value of AE, which is a half diagonal right here, and EC is the other half of that same diagonal, but that's not what I gave you here. AC is the length of the entire diagonal here. So in a case like this, you'd have to go ahead and put another 3x plus 5 right there for EC, and your equation now would basically boil down to the segment addition postulate. Little segment plus little segment equals the big segment. So in a case like this, we'd probably do 3x plus 5 for AE plus another 3x plus 5 for EC would equal the entire diagonal here, AC, which is 7x minus 3. So be on the lookout for problems like this where they give you the length of one of the half diagonals but also the length of the entire diagonal. And you can't just set 3x plus 5 equal to 7x minus 3 because then you'd be telling me that this piece right here was the same length as this entire diagonal, and that wouldn't make any sense. So watch out for that. All right, guys, that's everything we have there for section 7.2. So let's give that homework a try. Check your answers as you're going through it. Good luck, everybody.